if we're just dealing with two dimensions and we want to find the area under a curve, we have good tools in our toolkit already to do it. And I'll just remind us of our tools. So let's say that's x-axis, that's the y-axis. Let me draw some arbitrary function right here. That's my function f of x. And let's say we want to find the area between x is equal to a, so that's x equal to a, and x is equal to b. We saw this many videos ago, that the way you can think about it is you take super small widths of x, or super small changes in x. We could call them delta x's, but because they're so small, we're going to call them a dx. We're going to call them a dx. Super infinitesimally small changes in x. And then you multiply them times the value of f of x at that point. So you multiply it times the height at that point, which is the value of f of x. So you get f of x times each of these infinitesimally small bases. That'll give you the area of this infinitesimally narrow rectangle right there. And since each of these guys are infinitely small, you're going to have an infinite number of these rectangles in order to fill the space. You're going to have an infinite number of these, right? And so the tool we used was the definite integral. The definite integral is an infinite sum of these infinitely small areas, or these infinitely small rectangles, and the notations that we use would say we'd go from A to B. And we've done many videos on how do you evaluate these things, but I just want to remind you conceptually what this is saying. This is conceptually saying, let's take a small change in x, multiply it times the height at that point. So small change in x, multiply it times the height at that point. And you're going to have an infinite number of these, because these x's are super small. They're infinitely small, so you're going to have an infinite number of those. So take an infinite sum of all of those from x is equal to a to x is equal to b. And that's just our standard definite integral. Now what I want to do in this video is extend this, broaden this a little bit to solve I guess maybe you could say a harder or a broader class of problems. Let's say that let's go to 3 dimensions now, and I'll just draw the xy plane first. Maybe I'll keep this just to kind of make the analogy clear. So let me draw it. I'm going to kind of flatten this so we have some perspective. So let's say that this right here is the y-axis, kind of going behind the screen. As you can imagine, if I just pushed on this and knocked it down. So that's the y-axis, and that is my x-axis right there. That is my x-axis. And let's say I have some path in the xy plane. And in order to really define a path in the xy plane, I'll have to parameterize, I have trouble saying that, both the x and y variables. So let's say that x is equal to, let me switch colors, orange too much. Let's say that x is equal to some function of some parameter t, and let's say y is equal to some other function of that same parameter t. And let's say we're going to have t go from, t is going to be greater than or equal to a, and then less than or equal to b. Now this will define a path in the xy plane. And if this seems confusing, you might want to review the videos on parametric equations. But essentially, when t is equal to a, you're going to have x is equal to, so at t is equal to a, you're going to have x is equal to g of a, and you're going to have y is equal to h of a. So you're going to have this point right here. So maybe it might be, I don't know, I'll just draw an ordinary or random point here. Maybe that when t is equal to a, you're going to plot the coordinate point g of a. That's going to be our x coordinate. This is g of a right here. And then our y coordinate is going to be h of a. All right, you just put t is equal to a in each of these equations, and then you get a value for x and y. So this coordinate right here would be h of a. And then you would keep incrementing t larger and larger until you get to b. But you're going to get a series of points that are going to look something like, let's say it looks something like that. That right there is a curve, or it's a path in the xy plane. And you're saying, hey, how does that relate to that right now? What are we doing? Well, let me just try to see here. We're saying that's our curve, or that's our path. Now, let's say I have another function that associates every point in the xy plane with some value. So let's say I have some function, f of xy. F of xy. What it does is it associates every point on the xy plane with some value. So let me plot f of xy. So let me make a vertical axis here. We could do a different color. Call it the f of xy axis. Maybe we can even call it the z axis if you want to. there's some vertical axis right there. And for every point, so if you give me an x and a y and you put into my f of xy function, it's going to give you some point. So I can just draw some type of a surface that f of xy represents. And this will all become a lot more concrete when I do some concrete examples. So let's say that f of xy looks something like this. I'm going to try my best to draw it. I'll do it a different color. Let's say f of xy is some surface. I'll draw part of it. It's some surface that looks, let's say it looks something like that. That is f of xy. F of xy. And remember, all this is you give me an x and you give me a y. You pop it into f of xy. It's going to give me some third value that we're going to plot in this vertical axis right here. I mean, examples, f of xy. It could be, I'm not saying this is the particular case. It could be x plus y. It could be f of xy. These are just examples. It could be x times y. If x is 1, y is 2, f of xy will be 1 times 2. But let's say when you plot for every point on the xy plane, when you plot f of xy, you get this surface up here. And we want to do something interesting. We want to figure out not the area under this curve. This was very simple when we did it the first time. I want to find the area, if you imagine a curtain or a fence that goes along this curve this path. You can imagine this being a very straight linear path going just along the x-axis from A to B. Now we have this kind of crazy curvy path that's going along the xy plane. And you can imagine if you drew a wall or curtain or a fence that went straight up from this to my f of xy. So let me do my best effort to draw that. So let me draw it. So it's going to go up to there. Maybe this point corresponds to there. And when you draw that curtain up, it's going to intersect it something like that. Let's say it looks something like that. So this point right here corresponds to that point right there. So if you imagine you have a curtain, you could f of xy is the roof, and this is what I've drawn here. This curve, this kind of shows you the bottom of a wall. This is some kind of crazy wall, and let me say this point, it corresponds to. Well, actually, let me draw a little bit different. I want to draw. This point will correspond to some point up here. So when you trace where it intersects, it'll look something like maybe like that. I don't know, something like that. And I'm trying my best to help you visualize this. So this side, maybe I'll shade this in, make it a little solid. Let's say f of xy is a little transparent. You can see, but then you have this curvy looking wall here. And the whole point of this video is how can we figure out the area of this curvy looking wall? Right? This curvy looking wall. That's essentially the wall or the fence that happens if you go from this curve and jump up and hit the ceiling at this f of xy. So let's think a little bit about how we can do it. Well, if we just use the analogy of what we did previously, we could say, well, look, this, let's call this, let's make this a little change in distance of our curve. Let's call that ds. ds. That's a little change in distance of my curve right there. And if I multiply that change in distance of the curve times f of xy at that point, times f of xy at that point, I'm going to get the area. I am going to get the area of that little rectangle right there. Right? So if I take ds, my change in my, you can imagine the arc length of this curve at that point. So let me write, ds is equal to super small change in arc length of our path or of our curve. That's our ds. So you can imagine the area of that little rectangle right there along my curvy wall is going to be ds, I'll make it a capital S, ds times the height at that point. Well, that's f of xy. And then if I take the sum, because these are infinitely narrow, these ds's are they have infinitely small width. If I were to take the infinite sum of all of those guys from t is equal to a to t is equal to b, right? From t is equal to a, I keep taking the sum of those rectangles to t is equal to b right there. That will give me my area. I'm just using the exact same logic as I did up there. And I'm not being very mathematically rigorous, but I want to give you the intuition of what we're doing. We're really kind of just bending the base of this thing to get a curvy wall instead of a straight, direct wall like we had up here. But you're saying, Sal, this is all abstract, and how can I even calculate something like this? This makes no sense to me. I have an s here, I have an x and a y, I have a t. what can I do with this? And let's see if we can make some headway. And I promise you, when we do it with a tangible problem, the end product of this video is going to be a little bit hairy to look at. But when we do it with an actual problem, it'll actually, I think, be very concrete, and you'll see it's not too hard to deal with. But let's see if we can get all of this in terms of t. So first of all, let's focus just on this ds. So let me re-pick up the xy axis. So if I were to reflip the xy, let me switch colors. This is getting a little monotonous. If I were to reflip the xy axis like that, I'm actually only doing that same green, so you know we're dealing with the same xy axis. So that's my y-axis. That is my x-axis. And so this path right here, if I were to just draw it straight up like this, it would look something like this. It would look something like this. Right? That's my path, my arc. You know, this is when t is equal to a. This is t is equal to a. This is t is equal to b. Same thing. I just kind of picked it back up so we can visualize it. And we say that we have some change in arc length. Let's say this. Let me switch colors. Let's say that this one right here. Let's say that's some small change in arc length, and we're calling that ds. Now, is there some way to relate ds to infinitely small changes in x or y? Well, if we think about it, and this is all a little bit hand-wavy. I'm not being mathematically rigorous, but I think it'll give you the correct intuition. If you imagine you can figure out the length of ds if you know the lengths of these super small changes in x and super small changes in y. So if this distance right here is dx, infinitesimally small change in x. This distance right here is dy, infinitesimally small change in y, right? Then we can figure out ds from the Pythagorean theorem. You can say that ds is going to be, it's the hypotenuse of this triangle. It's equal to the square root of dx squared plus dy squared. So that seems to make things a little bit, we can get rid of the ds all of a sudden. So let's rewrite this little expression here using this sense of what ds is really the square root of dx squared plus dy squared. And I'm not being very rigorous, and actually it's very hard to be rigorous with differentials, but intuitively I think it makes a lot of sense. So we can say that this integral, the area of this curvy curtain, is going to be the integral from t is equal to a to t is equal to b of f of xy. Instead of writing ds, we can write this times the square root of dx squared plus dy squared. Now we at least got rid of this big capital S, but we still haven't solved the problem of how do we solve something, an integral, a definite integral. It looks like this. We have it in terms of t here, but we only have it in terms of x's and y's here. So we need to get everything in terms of t. Well, we know x and y are both functions of t, so we can actually rewrite it like this. We can rewrite it as from t is equal to a to t is equal to b. And f of xy, we can write it, f is a function of x, which is a function of t. And y is and f is also a function of y, which is also a function of t. So you give me a t, I'll be able to give you an x or a y. And once you give me an x or y, I can figure out what f is. So we have that. And then we have this part right here. This I'll put in orange. Square root of dx squared plus dy squared. But we still don't have things in terms of t. We need a dt someplace here in order to be able to evaluate this integral. And we'll see that in the next video when I do a concrete problem. But I really want to give you a sense for the end product, where the formula we're going to get at the end product of this video, where it comes from. So one thing we can do is, if we allow ourselves to algebraically manipulate differentials, what we could do is let us multiply and divide by dt. So one way to think about it, you could rewrite. So let me just do this orange part right here. Let's do a little side right here. So if you take this orange part, write it in pink, you have dx squared, and then you have plus dy squared. And let's say we just multiply it times dt over dt. Right? That's, a small change in t divided by a small change in t, that's 1. So of course you can multiply it by that. If we were to bring this part inside of the square root sign, right? So let me rewrite it this. This is the same thing as 1 over dt times the square root of dx squared plus dy squared, and then times that dt. right? I just wanted to write it this way to show you I'm just multiplying by 1. And here I'm just taking this dt, writing it there, and leaving this over here. And now if I wanted to bring this into the square root sign, this is the same thing. This is equal to, and I'll do it very slowly just to make sure I'll allow you to believe that I'm not doing anything shady with the algebra. This is the same thing as the square root of 1 over dt squared. Let me make the radical a little bit bigger, times dx squared plus dy squared, and then all of that times dt, right? I didn't do anything. You could just take the square root of this and you get 1 over dt. And then if I just distribute this, this is equal to the square root, and we have our dt out at the end, of dx squared, or we could even write dx over dt squared, plus dy over dt squared, right? Dx squared over dt squared is just dx over dt squared. Same thing with the y's. And now all of a sudden this starts to look pretty interesting. Let's substitute this expression with this one. We said that these are equivalent. And I'll switch colors just for the sake of it. So we have the integral from t is equal to a. Let me get our drawing back. From t is equal to a to t is equal to b of f of x of t times, or f of x of t and and y of t. They're both functions of t. And now instead of this expression, we can write the square root of, well, what's dx? What's the change in x with respect to time, or whatever this parameter is? What is dx dt? Dx dt is the same thing. Dx dt, let me write this down. Dx dt is the same thing, actually I should write it here, is the same thing as g prime of t, right? X is a function of t. The function I wrote is the g prime of t. And then dy dt is the same thing as h prime of t. We could say that, this function of t. So I just want to make that clear. We know these two functions, so we can just take their derivatives with respect to t. But I'm just going to leave it in that form. So the square root, and we take the derivative of x with respect to t squared plus the derivative of y with respect to t squared, and then all of that times dt. And this might look like some strange and convoluted formula, but this is actually something that we know how to deal with. We've now simplified this strange, this arc length problem, or this line integral, right? That's essentially what we're doing. We're taking an integral over a curve or over a line as opposed to just an interval on the x-axis. We've taken this strange line integral that's in terms of the arc length of the line and x's and y's, and we've put everything in terms of t, and I'm going to show you that in the next video, right? Everything is going to be expressed in terms of t, so this just turns into a simple, definite integral. So hopefully that didn't confuse you too much. I think you're going to see in the next video that this right here is actually a very straightforward thing to implement. And just to remind you where it all came from, I think I got the parentheses right. This right here was just a change in our arc length. That whole thing right there was just a change in arc length, and this is just the height. This is just the height of our function at that point, and we're just summing it, doing an infinite sum of infinitely small lengths. So this was the change in our arc length times the height. This is going to have an infinitely narrow width, and you're going to take an infinite number of these rectangles to get the area of this entire fence, or this entire curtain. And that's what this definite integral will give us, and we'll actually apply it in the next video.